So we're doing root finding. What is root finding? What do I mean by root? Root of what? We're not gardening here, so it's not a regular root. That could be one of the problems. Root of what? What does it mean to be a root of an equation? Pass to 0. So essentially, if I have a function, let's say that it's a function f of x is equal to 0, then the root of that function is x such that f of x is 0. Okay, so that's basically what solves the function f of x is equal to 0. Okay? I could have one, I could have multiple. I often don't know that. If it's a nonlinear function, there's no way for me to know in advance. Now, if I have a quadratic equation, such as a suggestion here, then I know that I have two, and for those two, I actually have a formula. Okay? So those two are not necessarily a problem to find because I have an analytical formula that gives me, I just plug numbers in, and I'm going to get the roots of quadratic equation. It's all other functions that are a problem. So what we were working with as one of the examples, not the only one, was the so-called parachute problem. So basically, there's this falling parachutist, just to give you a little bit of background, and I apparently have to do this every time. Swap displays. There we go. No. Once again. All right. So I have this problem of basically trying to optimize the shape of a parachute. And I need something called drag coefficient in there, which basically quantifies the resistance to the airflow that I have. And I know that my parachute works well if I actually find the balance between the gravitational force and basically the resistance to that motion through the air. So I have to figure out force balance or find where it is that I have zero forcing on the parachute, at which point the parachute will just continue inertially moving at the constant so-called terminal velocity without accelerating down to the earth. Okay? So that problem is a bit of an inverse problem because I kind of design the parachute and then work out how it works. So in order to get that coefficient, C, I actually have to plug in the forces and solve for it. However, that's not necessarily a simple equation to find the roots of. Okay? So if we plug in certain, so velocity is something that I measure. Okay? So if we plug in the values, I get something of this sort. Okay? So when I look at this equation, I pose my problem in terms of finding a root. So I'm finding V. So if I look at this equation, it's not posed as a root equation yet. This V of t is some function of c. And I do the algebra necessary to pose this as function of c is equal to 0. And then my problem is ready for numerical methods. Okay? So I have to formulate whatever physical problem I have in the form of f of something is equal to 0. So I'm looking for the root of an equation. Great. So now that I have this, what do I do? First step that we introduced is simply graphical. I could plug in some values and see what they are. And consistently plugging them in over an interval and then plotting the result would give me quite a bit of knowledge about the function. So if I do that in this particular case, this is how it looks like. Okay? So this is on the, I know a little bit about the physics of the problem too, so my drag coefficient should be positive. So I plug in a certain range of reasonable values and I plot my function. Right? And then I can simply see, hey, where does it intersect the 0? So that's visually, I can then see that, hey, it's somewhere just below 15. Okay? But as an engineer, building a bridge or building any structure that withstands time, you're not going to go with like, oh, it's somewhere below 15. Okay? That doesn't work. You got to find an actual number. So how do I zoom in on that number? I could again just keep plugging values. And if I actually look at the values of this function for c is 4, 8, 12, 16, and 20, okay? I will get, okay, there's something positive here around 34, then it goes down to 17 or so, around 8, then 12, which is around 6. Then I'm gonna, at 16, which is about here, I'm gonna fall negative. It's right here, actually. Okay. So I have a value of 12 and 16. One of them is positive, one of them is negative. In math, there's a theorem about this, but actually I can see that reasonably, without invoking a lot of math, if I have a continuous function between those two values, and I go from positive to negative, well, I gotta cross 0 somewhere. Unless I have some weird asymptote right here in between and the function is broken and not defined at the value in between those two. Okay? But if the function is indeed like nice and continuous in between, I gotta go through 0. Great. So this is going to be our heuristic. This is going to be our guiding light in actually devising an algorithm. What is an algorithm? What do we refer to as algorithms? I'm using that word a lot, and probably every time you hear it, you're like, oh yeah, algorithm. But if I asked you to define, what is an algorithm?
It's like a distinct set of steps that you follow to achieve some sort of end goal.
Right, and you have some reasonable proof that it's going to work, right? So it's a bit of a cookbook, of a recipe thing, right? So you follow certain steps, and you follow them all the time, and that guarantees certain type of result. So here, if I have a situation like this, and I know that the function is continuous, I can figure out an algorithm or a set of steps in a structured way to basically zoom in onto this value that I need. And that is basically what bisection method is. Okay? So here I start from finding two values, which I call a bracket, such that they enclose a root. And they enclose a root if one of them is positive and one of them is negative. So when I multiply those two values, I get a negative number. Okay? So here I have a positive value, and here I have a negative value. So the multiplication of the two will give me a negative number. I could have a reverse situation, so I could have a negative and a positive, doesn't matter. Still, if the function is reasonably continuous in between, I will hit a 0. So I can start zooming in on that 0. Okay? So that's first step. I gotta start from what we call a bracket. Okay? So I bracket the root, and in this case it's 12, 16. And then I simply, here's the algorithm. Okay, and I think you should be able to see why it should work by the end of me describing it. So if I do midpoint in between, that's 14 in this case, I split my bracket into 2. And now I just go and evaluate which one of the 2's follows the same rule. Okay, which one of the 2's contains that root. Okay? So I basically go and evaluate, hey, if I look at f of 12 times f of 14, which is, in this case, positive times positive value, do I get a negative number? No, so it's probably not a bracket. Okay? But if I look at the other one, I have a positive versus negative number, so f of 14 times f of 16 is going to be negative. So that's my next bracket, and it's twice smaller than the previous one. Yes? So that's the one I keep. And I just keep doing that until I'm happy with the small width of the interval, because my interval will keep halving as I go. Yes? So this first step of taking an interval, throwing in a midpoint, and then evaluating which one of the two halves is my next bracket is essentially the algorithm. And I just have to formalize it in terms of a loop. Which loop is good for this? Do I know how many times I'm going to have to repeat this? Not really. So a while loop would be good. So just keep looping in a while loop until my width of the bracket is small enough. So let's look at the example. If you were not here in class, or if you were here but you were not all that much paying attention because it was Friday and after exam, then open up that Lecture 5 RootFinding I posted it for you in files code. So if you execute that first cell, so the first one is actually just plotting this problem of a parachute. So I gotta import my NumPy and pyplot. Nothing is specifically difficult to understand and import here. And then I define my function f of c. So I simply define it and I call it f. And I can test it for a couple of values just to see what are the values that I get. And then I actually create myself a set of values c in between 4 and 20. And I evaluate that function and plot it for those values. And I also plot myself a zero line, okay? And by zeros, this is a trick to get a z of the equal size as my c, so I can plot c in those zeros, okay? And when I plot that, this is what I get. So you can just execute it. Again, this is just plotting this function. Great, so now I want to zoom in on this with this algorithm that I mentioned. So let's quickly walk through it. That's your next cell in this thing. So the left value, we start with left value of 12 and upper value, or left or lower, lower and upper 12 and 16. Okay. And again, next thing that I need to do, I need to basically do a half, bisecting half. Actually, this is a little more algorithmical. So find xr, that is the midpoint. And then for f of xr, go and evaluate. Is f of xr times f of xu less than 0? Or is it that it's f of xr times f of xl less than 0? Because basically that's telling me whether my left or right subinterval is my new bracket. Okay? And then I just replace things accordingly. So basically here, if this interval is the correct bracket, this was my xl, this was my xu. And now I have xr here in the middle. So if this is the correct interval, then my new xl becomes this xr. Okay, so my xl sort of moves over closer and becomes xr. Whereas in this case, if it was the other way around, then my new xu will become xr and get closer to the lower end. Okay, and that's essentially what is programmed right here. Okay. So I'm evaluating the width of this interval, and I'm giving myself width as 0.001 as something that is small enough. Okay, I'm decider of that. So I set it 10 to the minus 3 is small enough for me in this case. So if my absolute value of xu minus xl is larger than this width, so my interval is still large enough, I find the midpoint. I can print it. I should probably comment this. And then I go and evaluate. If f of xr times f of xu is less than 0, then my xl, new value of xl is xr. Otherwise, if f of xl times f of xr is less than 0, then my new value of xu is xr. Otherwise, well, I don't know what's going on. I'm going to just throw a warning. Hey, what's up for now? It is quite possible that I really hit f of xr, which is 0. Okay? In which case, neither of these will be true. It's kind of really low probability that I'm going to do that, but you never know. It is possible. So we can deal with that in a moment. Let's just now see whether this works. And then at the end, I'm just going to print these two values to see how close to the root did I get. Whoops. And I did not execute this first one, so we didn't know. Sorry. Gotta re-execute everything. And now again. Okay. So it is 14.7792, 14.780. Okay. Obviously, the difference between these 2 points has fallen below 0.001, which is what I'm asking for. And my estimate for the root, well, it's either this point or XR or that point. All 3 points are within 0.001 of the root. Which one you actually pick to declare the final winner for the 0 is really up to you, because they're all within this interval. Okay? So this is my root, and it seems to be graphically, it's close to what it needs to be here, which browser curiously always needs twice to execute. Okay? Since this point, that is 14.78 or so. Okay? Questions? So far, this is just a review of what we did last time. So this seems to work here. Okay? But the problem is that functions don't always come in this nice form. So we actually have to keep going. And I'm going to present a number of different methods, because not all of them always work. And you will, through your homework, see that it's not always the case that they work. So we have to have a number of methods at our disposal. The problem with this particular method is that it works when you have the bracket. But you have to go and search for the bracket. Okay? And that means that a human has to look at it. And if you're working on a Verilog that has 3,000 plus entries, you don't want a human to go look at every possible thing. You want things to be automated, right? As much as possible. And unfortunately, with RootFinding, that is not always the case. So whatever method that ultimately works is a combination of methods, typically. And it tends to work for the class of the problems that you're solving until you hit another snag. So let's actually now just quickly, before moving on, repeat this process with an alternative function. So you have the code that I gave you that works for that parachute problem. And now I want you to investigate this function. This function, mind you, is a cubic function, so it has it's a cubic polynomial, so it has up to 3 roots. Right off the bat, just by looking at it, I don't know how many. So first you will have to do graphical investigation similar to that bisection method. And then you will have to use the bisection method to find one of those roots. Let's go. And Ningir and I are here to help. And this is going to be sort of one of those quiz grades that you submit. So basically you can start with the code that I developed, just copy those and start modifying to work with this particular function. And this is also the example of code reuse. So technically, algorithm in itself is already programmed. You just have to tweak it a little to work with your problem.
numbers we're using?
Hmm?
Does it matter what numbers we're using?
And well, you kind of have to plot it and play with it initially. Graphical plotting, because I don't know what the ranges of these functions are. So just try a couple to see that you have sampled enough of that function and that you indeed actually cross zero somewhere. So this now becomes a different function.
Yeah.
Right? So you'll have to 12 and 16 is not going to be relevant to that function. It's going to be something else. So you got to play with it a little.
So that equation right there is the one that we're replacing.
You just want to replace this, yes. And then you have a different f. And the rest of the code, give or take mechanics of it, works. You just have to figure out which values to run it with. And this is also an example of code reuse. That's the code that you can reuse. Yes. Oh, okay. So you're just missing whether it was x cubed.
Yes.
Yeah, something. And I remember x cubed and a 2.5. How's that for helpfulness? So it is x cubed minus 5x squared plus x plus 2.5. And just in case I go away from that page. So what do you get when you plot? What do you get when you plot? Don't forget this is don't forget how power works.
C equals, it's just a range of values. So you can change that. You can change that to C is all. Because your C is just a range. That's just C. Yeah, I haven't.
All good? All right, go for it. Extra challenge for the bisection method part, create a function out of it that takes lower and upper x as an input and then works from there. And then you can play with it much more effectively, right? You can just execute it, assuming that your function f is defined somewhere in that same file, right? Because this one has 3 roots. Maybe you just want to go and find all of them, but you have to execute it 3 times for different brackets.
No. Figure out this.
Oh yeah, I got that. Second one.
Is that on the lens space?
Oh no, yeah.
But like they can sell it. They can do anything online. I mean, like I'm very angry now that they can't.
Oh, yeah.
Is your range like -5?
You always have to do it twice. I don't know why. Something to do with the browser. Wasn't me. I don't know. There are 3 roots. You want to find all.
We're just trying to find this.
She did the same because she did the same thing. So I may go and like talk to him and ask him about it. I'm not sure about so I'm going to
Are you guys planning on doing this?
She said that she was oh, maybe it was for today. I feel like part of the he said to go to yeah,
That makes sense.
Well, just look at the figure and you design it. Design it yourself.
And that interval is small enough that
And if you believe in it, it is. Just use an eyeball to fix that.
Yeah, that right here,
We're just taking pictures of their water.
and then right here. Well, that's,
So
So
this
we
one
have
is
3
under 4.
three roots in this.
and then this, so this one.
0 and 2.
How many of you have found at least one root?
Is this?
Yep. So, yes? Well, I asked you to find them. I didn't say anything. Yes. So this function, so if I just change this, I'm going to use C because it doesn't really matter how do I call these things. Is it plus X? Yeah. Is it plus or minus 0.5 plus? So these two values are not necessarily useful anymore. So I'm just going to do minus 2 to 20 and see what I get. Woo. C, F of C. Oh, X. And it's telling me nicely. Right. So this is how it looks like. That is a very bad plot. So obviously I don't need to go above 7 or so. So I'm going to stop here at 7 and replot. So this is just playing with it, right? And now I see 1, 2, 3 roots. Okay? 1 is between minus 2 and 0. Second one is between, I believe, between 1 and 2. Okay? And third one is between 4 and 6. Now, whether here you say 4 and 5 and 4 and 6 or 4 and 7 doesn't really matter. You're ultimately going to find it. So it's up to you to pick which one. But I'd actually advise to try to make a function out of this entire process here. How do I make a function out of this?
I just change a parameter from 4 to 10.
You can just change the parameters, but if I'm going to do that 3 times, this is the time where I want to define a function and just be more effective, okay? It's changing parameters still work, but basically I would say, hey, define bisection method, and it's going to have XL and XU as input parameters. And I'm going to, inside of this function, also count on F being defined somewhere before in the file, okay? So note that this function does need this. And I'm going to say, hey, this is going to be now indented. Okay? And instead of just print, I can print XL and XR. So this is actually X, I meant XU, sorry. So you have a little typo in there, XL, XU. I can just return. I can return XL, I can return XU, I can return XR. I'm gonna opt for returning one value and I'm gonna choose that midpoint. But do understand that whichever of those XL, XR, XU you return, you're within the width, okay, that you want it to be in. So now I could just say, hey, bisection method, and I'm going to execute it first with that, what was that interval, first one? Minus 2 and 0. Okay? And my output is this. And then I can just repeat with 0 and 2, was it? And 4 and 6. Do you see why it's now easier to have a function? Because ultimately, I can keep changing this and find all 3 at the same time. Again, you could have just created a script and changed the values. And again, note that this bisection method, it's kind of silent about the width it chooses. I could choose to have that as an input as well. And if you actually want to define a default value that if user doesn't enter anything, it's going to choose one for you, then you can say something like this. Okay? So this is a way for Python to just say, okay, if user doesn't enter the third value of width, I'm just going to use 0.001. Otherwise, you could choose it yourself. So let's just see that this indeed works. Yes, it does. But I could also go try to get closer to the root, right? Whoops. Or maybe not. What did I do? 3 were given. Apparently, do not forget to execute the cell. So in this case, I can actually see that I got closer within 0.0001, right? Because I chose to go with smaller width. So this is just a comment. So this is a way. I'm going to put is some arbitrary note. Note that the above definition within function input provides a default value for width unless user overrides it. Okay? Unless user overrides it. Does this make sense? So what I gave here is width as an input parameter if user knows about it and wants to use it. Otherwise, the function will choose 0.001 as a value to go with. That's what's called default. And comes in really handy. You have flexibility if you need it, right? If you choose to use your powers, you can do that. If you don't choose to use your powers, then you don't. Or you don't know how to. Yes? We're good? Okay. We're going to create, Ningyu, would you mind creating an assignment for uploading? So it's going to be bisection method for a polynomial or something like that. Okay, so let's now go back and actually comment a little on this method. This method is fine, but it can actually be slow. And it be slow because it actually uses no knowledge of function f, really. It just keeps going halving that interval until it reaches the value, which can be slow. And when I say slow, on all of the examples that we're going to try in class, it's going to be fine. But the problem is that if something takes 20 steps, and it could have taken 3 steps, that's 6 times more. And if you have something like 1 hour of execution of this method, that could be 6 times more, that's not negligible anymore. 1 hour versus 6 hours is a lot, especially if you repeat it a million of times. So in that case, we do want faster methods. And one of those faster methods tries to kind of second guess what the function f is. And it sometimes works if the function f actually really complies. And it sometimes doesn't, but it's worth trying. So what it does is actually say, okay, this blue thing is actually my actual function, which I don't know how it looks like unless I actually plot it and see it. But if I assume that I just put a linear function in between, just a line, as an approximation of this function, as I'm getting closer to this root, I'm actually just, how about I just take root of that linear function? And maybe I'm closer to my root than just going and halving the interval. That's the idea. Does it always work? No, and there's unfortunately no guarantee in these, so we just have to kind of give a variety of methods that do different things. So if I do geometry analysis of this, these two triangles are similar, okay? And basically the length of this divided by length of this is the same as length of this divided by length of this. I also carefully look at who is positive, who is negative to make sure that this works. And basically I get something this, and from here I can actually get a new or alternative value for my XR. I'm going to replace it with this point here that I can work out from this equation. And when I do that, this is actually what this XR should be. Okay? So essentially, I can actually just replace the choice of this midpoint XR and have the same problem as I had before, just using this XR. Okay? So instead of my bisection method that just went with the midpoint without looking at the function at all, it just said, hey, just choose a midpoint. Okay? Here I'm saying, hey, let's do an approximation to this midpoint or this root that is possibly closer to the root than the midpoint. And from that geometry analysis that I just described, I get that this is what this approximation should be. Okay? Can you see if it works? What do you need to change in just previous? We actually have precisely enough time to do that. So if I wanted to make this, I do a good old copy. And then I go to my new cell. And now why is my scar? What? Okay. So now I'm just going to call this false position method. So what do I need to change in this false position method to make it a false position method and not bisection anymore? So instead of midpoint, what do I need to write down? This. Okay? So let's just do that. XU minus f of XU times XL minus XU divided by f of XL minus f of XU. That should be it. Other than that, so method is just estimating this new way to bisect the bracket in a different way. And this is the only thing changed. And this is again one of those code reuse where I had the method that worked before and I just, so let's see if it actually works. So now I'm going to do false position method. Minus 2 and 0. And I'm going to compare it to bisection method of the same. So I'll see what are the values, and let's see whether I had any typos in my code right now. Moment of truth. Anyone? Okay, I need to say print. Oh, it's still working on it. Something's wrong. Stop. So when you see a star here, it's working on it, and it went onto a loop. So one thing that I'm going to do here, I'm also going to institute something saying, because this one sometimes has trouble converging, So I'm going to institute a maximum number of iterations as 10,000. And what I'm going to do is I'm going to, no matter what, I'm going to stop after 10,000 iterations. This is typically a good practice. And I'm going to count the number of iterations. So initially it's 0. But the moment I enter the loop, I say, hey, increment my number of iterations. And let's be intuitive. There's quite a good chance that I had a typo. I'm going to double check in a moment. But again, this is not a bad idea because sometimes methods do not converge properly and you do want to stop the number of iterations. So good idea to have an upper bound on iterations just in case there are convergence problems. Convergence is, are you successfully getting to that root or any solution of the problem? Okay. Let's try now. It should still stop. I need an and.
And instead of or.
And. Both need to be true. So if this keeps not getting better, okay, then it's going to stop the moment this stops. With or, it wouldn't stop. Apologies. It's still not stopping, so I still have some debugging to do. And we're going to fix that next time. In the meantime, you will submit your bisection method for that polynomial. Okay?